Welcome to this one more lecture on the scattering theory. And in this particular lecture, we will see the asymptotic limit of Lippmann-schwinger equation. What is the meaning of asymptotic limit? We just have to approach the R tending to infinity. Why we are doing that? Because the detector is very far from the target, right? So it is just to give you idea. We are doing scattering in the, let us suppose, metal foil, and the scatterer are just the small nuclei, which is of 10 to the power minus 15 meter. And let us suppose that somewhere 10 centimeter away is the detector. So that 10 centimeter is very big in comparison to 10 to the power minus 15, the size of the scatterer. So here the r dash is just to give you the idea of the size of this target, the scatterer, right? And this r is that 10 centimeter, which is the distance from this target to the detector. So this particular distance in general, right, in most of the cases, is very large in comparison to the size of the target itself. So we are interested in the asymptotic solution by assuming this particular r to be infinity. Infinity not in the literal sense, but it is just to get the mathematical idea, right? So what we have to do, we just have to calculate the asymptotic limit of the Lippmann-schwinger equation. So we have derived this particular equation in the last lecture, right? And we just have to put this particular limit, which is r is very greater than r dash, or you can say r is tending to, you can say, infinity. So what you have to do, you just have to take this particular approximation, and you have to calculate the first value of this particular multiplication. So k into the mode of r minus r dash will be k into, it is because the mode, which is the distance, this particular distance, which you know by using the basic physics or basic mathematics, you already have studied that it will be square root of r square plus r dash square minus 2r vector dot r dash. And you just have to take r square as common, right? It is just the power half, and when r square will be common, so that from that particular bracket r will be out of that particular bracket, and inside you will have 1 plus uh, this particular quantity divided by r square, right? But we have assumed that here r square is very greater than this greater than this particular quantity, so we can use the basic limit approximation, and this particular expression will be this expression, the approximate value of this expression will be this. It is k times r into 1 minus r dot r dash divided by r square. Why? Because this particular expression we have just neglected, right? Because it is very small in comparison to the other expressions, and this is minus, right? And this particular half has been divided in this particular, the 2 has been divided, or you can say half has been multiplied with this particular expression in the limit in the series expansion, and this 2 has been cancelled, so this particular term is just this. And you can just multiply these terms inside the bracket. It will be k times r minus k times r will cancel to this particular r, it will be this, and this vector divided by the magnitude, it is just the r direction. And when you apply that r direction with, you have that r direction with k, it is just k vector, right? So k vector is r dot r cap, which is k dot r dash. R dash is just this particular position of this point source. I have explained you in the previous lecture about that, right? Now this is what the approximate value of this particular expression, which is kr minus k dot r dash, and the approximate value of 1 over this particular quantity is just very simple. So it will be 1 over just r mod, because this particular quantity we are assuming to be very small, right? So the approximate value is 1 over r, right? Now you just have to put these approximate value in this particular Lippmann-schwinger equation. So that equation will be just replace this particular expression by this particular value, and 1 over this particular expression 1 over r, and it is just the basic calculation. You just have to separate these this exponential for these two powers, and it will be like this. What we did is that we just have taken e to the power iota kr as outside, because the integration is with respect to the r dash, so we can take this particular expression, because it will be act like, it will act like the constant, so we can take it as the factor, or we can take it out of the integral. So we have did, and this r can also be taken out, and the remaining portion is e to the power minus iota k dot r dash. So it is e to the power iota k dot r dash into v of r dash and psi of r dash dq r dash. And this particular expression you can assume as the expression of theta and phi, because when you will integrate this particular expression you will get the expression in theta and phi. Okay, even you know that this expression looks like that it will be in r dash, but in reality we have solved this kind of expression already, right? You will get the final expression will be dependent on theta and phi, the direction, right? And that's why we are writing this particular expression as theta and phi. So this expression can also be written in this form, where this phi of theta, sorry, f of theta and phi will be equal to this particular expression, which I have written here, right? And if you just look at this particular expression, it is the expression that we have assumed, or we have just calculated intuitively by using physical intuition in the second or third lecture that I did on this scattering theory, right? So this is the same expression, but now this time we got this by using mathematics, by using the asymptotic form of Lippmann-schwinger equation. And this f of theta and phi was defined to be the scattering amplitude, and this was the quantity that we are looking for, right? And I also derived this particular relation, which is the differential cross section is equal to square of mode of the scattering amplitude, and you just have to take mode and just have to uh, take square of that particular quantity, and it will be the scattering differential cross section. So this way, by using Lippmann-schwinger equation, we have just calculated the expression for scattering amplitude, and we have calculated the expression for differential cross section. Yeah, of course, until we know this particular expression, we cannot solve this particular equation, and we don't have anything. But we will apply Born approximation to just calculate some solution for this particular equation to get this scattering amplitude. But this is what we have got by using the Lippmann-schwinger equation, and this is the asymptotic solution. Right? This is the asymptotic solution of Lippmann-schwinger equation, which is the incoming plane waves and outgoing spherical kind of waves. Right? This is the same expression that we got by using the physical intuition. So this is it in this particular lecture. Thank you.